I will take you on a little journey with Spinnaker 2 and give you some tutorials here and a small introduction. So you see the board standing right there. It's a single chip board. And at first, I would like to give you some introduction on the software stack, what we have here in the repositories, which is mainly maintained in GitLab. So there's this presentation is intended also to be a little lookup. If you want to do something yourself later on, then you can follow the links, and I put some information on there what you can do. What you see there, there's documentation on the Spinnaker 2 here in via gitlab.io, and you can basically click through there. You have a little overview on the general architecture. You have a little introduction. What's here in the hardware, you can basically use this to set up your first application here. And there's some information on this and on more specific things, like, for example, DMA access. You will also find some information here. So this is a good starting point if you want to develop something by yourself on Spinnaker 2. Let's go back to the slides. The main libraries that you will probably use at the beginning is S2's Sim2Net app. That is the one library for basically low-level programming Spinnaker 2. So there's the host software in C++ and the software for the chip that's running on the processor elements that's written in C. So if you want to write some tests in C and C++, this is the one you need. You need it anyway, also for PySpinnaker 2, which is a Python-based library. And that's basically a Python interface for running spiking neural networks on Spinnaker 2. That's the original use case. What I use it for, it's also quite nice with this experiment runner to basically interface it, to have a high-level interface from Python to the chip. Because you have some abstracted functions there for simpler interfacing with the chip and simpler execution. For example, you can see this here, sending data to the PE. You simply have a function add memdata to send, which you simply add to a configuration for the PE. Maybe to repeat this or to say this first, the PE is one of the processing elements within the chip. So let's go to the documentation here. If you have, this is basically the Spinnaker 2 chip, and on there you have 152 processor elements that you can freely program. They're based on ARM Cortex-M4 processors. So each of these nodes here is one ARM Cortex-M4 processor, and this is what we consider a processing element, a PE. So each of these 152 processors, you can configure them independently. You can set data there. You can add regions where you want to read from the SRAM of the PEs. You then put this into a configuration for the PE, and you basically add this configuration to an experiment here. This experiment is then, you simply call it via run, and then your C code gets compiled, loaded onto the processor elements within the chip, and it gets then executed. And you can basically then read out the results from Python. So as for Sim2Net app is if you really want to do all the C and C++ interfacing by yourself. If you want a bit more comfortable access via PySpinnaker 2, it's also nice to really interface from Python, and you can use the experiment runner for this. Then there are a couple of repositories that's currently being worked on. So you will get a little overview here, what we are working on at the moment. There's Spinnaker 2ML. That's the long-term baseline for the DNN software stack. So there are already a couple of functions integrated, but there will be more functions integrated, and it will serve also as a base for the scheduling. And it's required for some abstracted functions that you might also use, like DRAM access. So besides Spinnaker 2 chip on the board, you have a little DRAM. Little means 2 GB. And if you want to access the DRAM from the chip, you might want to use those abstracted DRAM functions. For this, you would also need this Spinnaker 2ML. There's a bit older project as an endpoint to Spinnaker 2. That was originally a project where you can convert directly from SNN torch to Spinnaker 2 executable setup, and but this was without neuromorphic intermediate representation, so it's direct conversion from SNN torch to Spinnaker 2. The current development goes this way via NIR. So everything, at least what I know at the moment, that's going on in this direction is always via NIR, and this is then within the project PySpinnaker 2, which I mentioned here on the first slide. So it's a bit centralized at the moment. Then there's Octopus Scheduler. This is what I'm working on relative or intensely. This is basically an on-chip scheduling framework. So you for deep neural networks, non-spiking deep neural networks on Spinnaker 2. So it's basically used, for example, for this vector matrix multiplication, like in the Rakoff model, to partition this for the single processors, map it to the processors, and then execute it, read out the results, and get a time measurement. It's intended to extend this for complex DNN architectures, which is work in progress at the moment. Yes, and then there's Spinnaker, the one at the bottom here. So this is a framework that people who have been using Spinnaker 1 might be familiar with. And this is at the moment ported from Spinnaker 1 to Spinnaker 2. So that people who are familiar with Spinnaker 1 development can then use this interface also for Spinnaker 2. It's also work in progress. So now you have a first overview what's there. I mean, it's probably a bit much information right now, yeah. So the most important ones are really this S2Sim2 Lab app and PySpinnaker 2. These other ones might be interesting for you if you want to do specific things, and it's rather a lookup. If you want to look at these slides later, you can use this as a starting point. Now I would like to talk a bit about my work. So this is the on-chip scheduling for non-spiking deep neural networks. The project has the nice name Octopus Scheduler because it basically orchestrates the processor elements like in Octopus. And the basic principles here, I will go through this very quickly. What you have here is again this view on the 152 processor elements on Spinnaker 2. And one of these processor elements, so one ARM core, is the scheduler, which orchestrates the workers. So we have 151 remaining workers. Typically, I map the deep neural network layer to a number that fits the partitioning so that you have even partitions. So typically it's like 128 workers or 144 workers that are used for the layer. The way it's implemented, the scheduling approach, is via a finite state machine in software. So you basically have a state machine. I will show this a bit later, where you iterate through single states, like execute matrix multiplication, execute accumulation, fetch result, write results to DRAM. These are all single states. And there's a certain way how the state transitions work there. And this is entirely controlled by the scheduler for all the workers. So the scheduler has an overview what state the workers are currently in. And then the workers always execute the current state, like the matrix multiplication. And this is how this looks like. So you have the scheduler node and the worker nodes. And there's a centralized control from the scheduler to the workers, but only for the states. So you don't have a lot of data communication going on between the workers and the scheduler, so that it's not a bottleneck. And this is really only control words like state transitions, flags to start a certain instructions, and then the worker responds after it executed an operation. It's just that it has finished the current state. Decentralized is the data transfer. So this is not going via the scheduler. This is going directly between the PEs. If you want to fetch, for example, partial results to another PE to accumulate them or something like this, this is decentralized again, so we don't create a bottleneck. And this happens directly between the PEs here. How does this look like? So how do I basically construct such a state machine from an operation? This is an example of a matrix multiplication where you would create these partial products. So you tile the matrices and partition them. And then you multiply the tiles to create one partial product. And you would create, or you would use another partial product and accumulate this. In the scheduler, this partial product here would be executed on, for example, processor 1 and on processor 2. So on code 2, you would create this partial product. You could fetch this to the processor 1, accumulate it, and you have the final result for your output tile. What states would this result in? So we always have the default states from an idle state. Then you realize that one of the processes finished. And after the layer has been completed, you realize that all processes have finished, which is basically the information that the layer has finished. For the actual instructions where the worker actually executes an operation, you have the matrix multiplication, you have fetching, and you have the accumulation. And if the matrix gets larger, you might not be able to compute the full output in a single run. So you might only be able to compute an output tile. And then you have to reload some input data, compute the next output tile, and so on. So then you also need to the DRAM access within the layer. So you need some DRAM read instructions and some DRAM write instructions. Then you can use these states and put them into a state machine. So you always start from an idle state, then you load some start addresses, you load the input operands, execute matrix multiplication, then you might fetch partial results, accumulate, store partial results that's only required for debugging, or store the final result. You might then iterate again if you have other output partitions to compute on, and then eventually store the final result here, and then they're finished. So that's basically for an instruction like this, how these state machines are constructed. And currently I modified this because it turned out in the measurement that this SRAM fetching and the accumulation consumes quite a significant amount of time. So I'm not doing this with partial products anymore, but I'm really taking one block of input data and multiplying it with one full block in the height dimension with the weights basically. So I'm not creating any partial products that I need to accumulate. I'm always computing a smaller tile of the output, but I spare this fetching and accumulation. So this was to make it more efficient. And that's the rough algorithm here for the worker. So it's really relatively simple if you break it down to an abstracted form like this. And you basically always receive an interrupt from the scheduler. So the worker knows that it needs to do something. You then execute a task dependent on some flags. So if the flags are start matrix multiplication, then you execute the matrix multiplication and then modify the flags to, you set a bit that the matrix multiplication finished, and then you send the updated flags to the scheduler. So the scheduler knows what the worker has finished and what he's currently doing. The scheduler is a bit more complex. The way I implement this currently is via a big for loop, which is not very efficient. I will explain this in a second, but this is the first implementation. Basically, the scheduler always has an array of the current and the previous state of the workers, and it iterates over each worker if the state or if the flags actually changed. So if an operation has been finished, then the scheduler knows that it needs to do a state transition for this worker, and then it triggers the worker to execute the next operation. Why is this inefficient with a for loop? You can imagine if this is your array where you have all the workers. If this worker here updated its state recently, and the next worker to update its state is the one just above in this array, then you need to go through all the workers. And this potentially means that you have a relatively high delay until it's the next worker's time to update. And I also saw this in the time measurement. So because it's not really, it depends on the execution time on the chip, how this sequence of updating actually goes. And I saw in the measurements that basically this time for updating the worker state has the highest variance because it basically depends on the execution order. And I want to get away from this eventually, and I want to use really interrupt controlled updates here. So the workers have a direct interrupt to the scheduler, might need multiple schedulers for this. So you don't have to iterate over such a for loop, but you really have a direct interface for the control between the workers and the scheduler. This was a rough overview over my work here, what I'm doing on Spinnaker 2 at the moment, mainly. And now I would like to give you a little introduction with the Spinnaker 2 coding, some information on tutorials, documentation, and low-level functions. So this is again a collection of links. If you want to do something, these are points where you can get started. It's again referencing to the Spinnaker 2 documentation in the skitlab.io. And you have a nice overview here over the chip architecture. We already took a look here quickly. So this is the most important things you need to know about the chip architecture. Then you have a getting started here for your first application. It basically tells you how to install everything, what you need. There's also a Docker container in S2Sim2Lab app, which helps you to install these things, because it's a couple of things that you need, like digital runtime and so on. So you can use the Docker container for a simplified installation. Yes, then the first test case that you would start with is always this ARM sanity that basically just lets a single processor on the chip return a value and lets the host read out this return value. And if it's the value that you expect, it's a success. So this basically tells you how to operate this test case and what it should look like once you've finished. It's probably not, you can probably not see this very well, but it says passed. So if it says passed, then this means you successfully connected to the board, successfully run the test case, and everything is working nicely. We will also go through this a bit later on. Then you can see the extra test case execution on the board. There's also tutorials for controlling multiple processors. Yeah, if you want to take a look at this, you can read through this. And for DMA, so the DMA is required for accessing the SRAM from one processor to another. So each processor has its own SRAM, and if you want to access information in the SRAM of processor B, you want to access it from processor A, then you would use the DMA here. And this is documentation how you could basically access another PE's memory SRAM, or how you could access also the DRAM interface, for example, for larger files or larger data, or larger amount of data that you would need to load within the execution, like for this larger matrix multiplications. Now here, this refers to this project S2Sim2Lab app, and I will quickly go there. So we have project S2Sim2Lab app. And if you want to access this, you need to request access. So this is not public at the moment. It's you need to be granted access. Bernhard Wogginger is doing this at the moment. And yeah, so you need to drop him a mail that's written in the Spinnaker 2 documentation in skitlab.io. You need to drop him a mail if you want to access this code and if you want to play around with these low-level functions here. So there are several test cases in this project, and I would like to show you a bit around here. So as you see, there's plenty of test cases. The first one you would always start with is this ARM sanity, and as you can see, it's as simple as it can get. You just have a return value here that you simply return from your single processor and then read it out from the host. This is the chip code that's running actually on the processor, and then you have the host code. That's the code for your laptop if you're connected to the Spinnaker 2 board, for example. And you would then have this TC S2App ARM sanity, where you basically have this, you set up the connection here, and then you check the return data and yeah, basically check if it's the value that you would expect. You have other test cases for these low-level functions. One important one is the rec file interrupt. So let's go back here. The rec file interrupt. Here, rec file IRQ. This is important, for example, to synchronize the PEs between each other. So if you want to trigger a processor from another processor, you would use one of these rec file interrupts, for example. There's also a test case for saving power, so sending a processor to sleep. That's one of these test cases here, and you would use, because the processors are all ARM cores, you would use one of the ARM intrinsics here with this wait for enable. And you could then trigger the processor again to do something with an interrupt, for example, where you have this interrupt handler here. That's quite important for low power operation, that you send the processors to sleep if they don't do anything. There's a test case for the matrix multiplication. Oops, sorry. Using the machine learning accelerator. That's one of the dedicated accelerators that Christian was talking about. That's new on Spinnaker 2 compared to Spinnaker 1. This is the machine learning accelerator, which has a mode to support matrix multiplications and convolutions. And one test case where you could see how to operate this, how to configure the processor, is this test case matmul all PEs here. And we can take a quick look here. This is how it looks. Now it gets a bit more complicated because you have all the configuration here for the machine learning accelerator, where you specify the dimensions of your metrics. And you then also, you can use the machine learning accelerator for 8-bit or 16-bit inputs. So you would need a quantized input. You can use it signed or unsigned. You can integrate a shift value if you need to, if you're sure, or if you assume that the output might have resulted in overflow, then you can already shift it before the output. It has an integrated value function, so without any additional cycle, you could execute a value function after finishing your matrix multiplication or convolution. And yeah, that's about the most important things here. You have a similar test case for the convolution, where you can also see how you can configure the machine learning accelerator. That's then the conf2d of all PEs, and you will see again basically your struct, where you have all these parameters from the machine learning accelerator. You have a couple of more parameters here, and these are basically the parameters where you set the dimensions for your convolution. One thing that's rather important is the data alignment. So it's a 16x4 MEC array executing multiply accumulate operations, and some of these parameters here need to align with the dimension 16 or 4. For example, for the convolution, it's the output width that needs to be a multiple of 16, and I think the output channels, that needs to be a multiple of 4. And for example, here the stride is always a power of 2. So possible strides are 0, 1, 2, 4. A stride of 3 is not configurable in the machine learning accelerator, but that's a rather rare use case. I mean, typically you have strides of 1 and 2. So that's the things you might need to configure here. Okay. What's also nice to have, what you use, for example, for a synchronized start of all processor elements, or to communicate from the host to the PE and have basically the PEs know that the host is communicating with them, is a global interrupt. And you can find a short test case for this in the global IRQ Ethernet. How does this look like? You basically have an interrupt handler here. It's depending a bit on the position of the processor. So the processors on the Spinnaker 2 chip, they are grouped into groups of 4 PEs. So you have to make sure here that you get the right interrupt. And then you basically have this here, the sleeping function, wait for interrupt. And when an interrupt from the host arrives, such a global interrupt, then the PE wakes up again. So there's 2 types of interrupt, 2 most important types of interrupt. One is the global interrupt for the host to PE communication, and there's the rec file interrupt that you can use for communication between the PEs, for example. that was probably a bit dry. So I would like to get into the actual tutorials now with you. And I prepared several for them. Sorry. The first is really this ARM Sanity Ethernet test case. And that's the simplest test case where you just read out the return value and check that it's actually the value you would expect. And so the thing we can do now is to actually use a command line. And I would like to demonstrate you quickly what you need to do to execute this test case. So we go into STSIM2NetApp now, and we have the chip folder here. We go into the correct path, and then you have all the test cases where I showed you something right now. And the one we want to look at is the ARM Sanity Ethernet, because the board is connected via Ethernet. And we go into this one, and then we run make export. That's compiling the C code for the ARM core and exporting the files in the correct folder for the host where we later compile the test case. So this, now you can see that the compilation here of this ARM code basically worked, and that it exported the compiled code into the correct directory for the host, which is where we go now. So we change into the host directory. And now you have here kind of a replicate of this folder structure. And where we need to go is always in this TC and then S2app. And then we have the same name here. So this ARM Sanity Ethernet. You have the test case here, another makefile, and in this program, you will find the file that we just compiled here. And now we run a make run in this folder. This basically compiles the host code, which puts the code onto the PE and executes the test here. And you see that we read out the value that we expected. And we have a nice pass here with a nice stack. And this is what you would expect from this test case. So we see now that the basic connection here between the host and the board is working. And we can look at another test case, jumping a bit in complexity. So that's the SNN, the direct implementation on Spinnaker 2, and the execution on a single chip. So let me quickly take a look here. And we want to go to the PySpinnaker 2. And so this is one of the projects I was talking about previously, where you have this experiment runner and you can execute SNNs. And I now go to the examples folder, where you will find a folder called SNN. And we can quickly take a look at the LIF neuron, which is the simplest test case here, I guess. Oh, oops, sorry. That was not expected. Okay, there we go. So this is how this test case looks like. You have a couple of input spikes here. You create an SNN population with a neuron model. You configure some of the neuron parameters, and then based on the LIF neuron here, you create a population for this SNN, and then you create some connections here, some projection, and you basically then define a network where you add this population and the projection. Then you define your hardware, which is the Spinnaker 2 chip with the according IP address here. You specify a number of time steps, and then with this function, you execute this on the chip. And I actually want to go to another. Let me go here. It's the wrong one. video. And so we need to later. This one. Yeah, nice. Okay. And that's basically the Python script here we just looked at. And I will now execute this on the chip. So we configured the IP address here, and this will simply execute this SNN, this very simple SNN here on the Spinnaker 2 chip. You will see a lot of information here. So what you can see is that it uses 2 of the 152 PEs here. The simulation time is 50 milliseconds here. And then you see a lot of debugging information, a lot about the write statements here. And at the very end, you can see some more information here. Basically on the addresses of your population table. And you can see some more information like the number of neurons you used and so on, and then which neurons spiked at which time. And what we did then at the end was to read out spike record and the voltages. And this is what you can see here in this nice little graphical visualization. So you will see the input spikes at a certain time step. You would see the voltage of the LIF neuron, and you would see when it creates output spikes. Yeah, so that's it for the simple SNN test case, how you would basically define an SNN with neuron populations just in PySpinnaker alone. Let's get a bit more complex with the ANN to SNN example. So you would basically take a non-spiking ANN, convert it to an SNN, and then execute it. So this is, I quickly have to take a look. This is also in PySpinnaker 2 in the hybrid path here. It's an MNIST example. So basically an example is created for a CNN on MNIST dataset. And let's check out the file here. It's the snn.py. And you can see here that we load just a trained CNN model here. And then you create basically, or you get the weights from this model, and then you create your populations here. Input population, another population here for the hidden layer. And then you basically take these weights and assign them to the connections in this SNN. And you then define a projection here between the populations. You again define your network with your populations and the projections between the populations of neurons. You define the hardware as the Spinnaker 2 chip with an IP address, and then you call this hardware run again. Let's execute this example. So you see some TensorFlow because it's loading the model here. I will go up quickly again to look what's actually going on here. Now it's checking out the MNIST data set. You always have some text at the beginning for Spinnaker 2. You see it's trying to get the UDP transfer running. You see this information here again for debugging. And then you see some readout information here. And at the end, you see that there was one spike here recorded. You read out some spikes, read out the voltages. You see again the duration of the recording, and you see the predicted label and the actual label, and that it's the correct prediction of what came out of the SNN compared to what was expected. So this was an example how to load data from an HDF5 file, classical Keras or TensorFlow model, how to integrate it with Spinnaker, and how to define your own neuron populations, map weights, and then execute it as an SNN on Spinnaker. Let's get a bit more complex. So this was now you take directly ANN, convert it to Spinnaker, and execute it. converted to an SNN and executed on Spinnaker. Now there has been some really nice development, I think last year at the Telluride neuromorphic workshop with the neuromorphic intermediate representation. That's basically there because there are different frameworks you can train in and different hardware platforms you might want to run your algorithm on. And this is an intermediate representation where you can basically go from different training frameworks then to different hardwares. And this example here, I quickly want to show you this. This is the documentation of this neuromorphic intermediate representation. Reading the docs is always a good idea. And what you have here is this general documentation, and you can find here on the left, for example, information on Spinnaker 2. So you have the definition here, how you would create simple graph in this neuromorphic intermediate representation. And we are not yet taking a training framework, but we're directly creating a graph in this intermediate representation, and then importing this to Spinnaker and executing it on the chip. And this is how this looks like in a complete test case here. So we take this example, it's basically code from this website here, yeah. And you define your graph in this neuromorphic intermediate representation within the Phenom layer, which is basically a fully connected layer and some LIF neurons. You save this as a model. You read the model again. You have to make sure with this inferior types that the input and output nodes also get the correct types. And you then have this conversion configuration, which is required between the conversion between NIR and Spinnaker 2 framework. And then you do the actual conversion. You define, in this case here, a random set of input spikes. You again define your chip here with the correct IP address, and then you call hardware run. And this is how this looks like here, basically. You see again, we're writing stuff to the chip and sending information there. And we can see that we're running this experiment here for 63 milliseconds. And you will now get some information from the single PEs that we're running it on. I think it's 2 PEs here. And it's running on this PE with coordinates 110 and 111. And in the end, you will read out some spikes, and you can then read the spikes and voltages again. So this is a short example here, how to go from this neuromorphic intermediate representation to Spinnaker 2. The next step would be to train your own model, your own SNN, using a framework, for example, like SNN Torch. And I basically combined the information here together from the really nice tutorials that Jason created for SNN Torch. There's a quick start tutorial. It's a Colab Jupyter notebook here, and it's also for analysts. So you would have first some transformation here, then you define your model. I'm using a smaller one here, and because this convolutions here still need to be integrated in this SNN Torch to NIR conversion. So I'm using a simple NLP for the classification. And then you have your training loop. And I will then, after this training loop, take the trained model from SNN Torch, store it, read it out again from this neuromorphic intermediate representation, and run it on the chip. How this looks like in a complete script is you have some parameters here. You create a network here that's based on linear layers and leaky integrated fire neurons. No, sorry, leaky neurons here. You have your classical forward path. You have your transformation, as we saw in this notebook by Jason. You load the endless data and set some training parameters here. You then have your training loop. And then there are, I just take, because I just want to show the integration from SNN Torch to Spinnaker 2, I just take some random input here. You have the NIR export, read it again, and you have to do this inferior types again, which I didn't do at the beginning, then it fails. So you always have to do this. It's important for the input and output node to get the correct dimensions from the other nodes. And you have again your conversion configuration. Like in the previous example, this is the actual conversion from NIR to the Spinnaker 2 shape. And then, yeah, that's okay, sorry, that's the random input here. And you define the IP address for your chip. And then you could also, for example, use the Brine 2 simulator. If you don't have the chip here, you could use this for simulation. Or in this case, we're using the actual chip with the IP address and then running it on the hardware. And you will get some output drawing here, which doesn't make any sense because I just feed random data to the input. So this looks like this when we execute this. We're now downloading NList because it's a temporary folder. That speaks for the quality of the Wi-Fi connection here. And we're now training our really stupid little SNN. It's just a single or 2 layers fully connected basically.
Is that training on Spinnaker right now?
No, it's training via SNN torch on the CPU.
I see.
Yeah, on the host. So we achieve a record-breaking accuracy of 95% on NList. And what you can see here now is that basically these we're executing it on 2.
So in terms of learning, you've got stuff like eProp, event prop, that we also implemented in Telluride, command synaptic sampling, deep R, so a couple of the verified ones.
That will run on chip.
Yes, exactly.
Okay, that's nice.
Plus stuff like what we recently did with block local learning, that's also going to be implemented in the future. So you can actually do serious DNA training, also multi-layer training there.
And how does this kind of stuff transfer to Spinnaker? Like if you do it on SNN torch and then you run the exact same thing on Spinnaker, like you've got 95% here, what might you get on Spinnaker? I guess we'll see in a second.
No, because it's just a running input, just to see the flow really. So yeah, I mean it's basically a floating point operation on the processor, and your standard way to execute the SNNs on Spinnaker is also using floating point. So on the ARM cores, you have the floating points instructions, and since it's floating point on the host and floating point on the chip, you should not have a difference there. If you want to speed up the processing, which is what Jennifer did with the machine learning accelerator, you would need to quantize the information, and then you would probably have a difference in the accuracy. Yes, so this is really just for the flow, how to get from SNN torch to the implementation on Spinnaker 2 with a random input here. And at the end, you see that we can read out some spikes again and some voltages. And this is just a, yeah, it doesn't make sense here, but you can see the output neurons from class 0 to 9 spiking. I mean, it should just be one class for one sample, but I'm just providing really random input data there and observing it for a couple of time steps. You can see the neurons spiking, you can see the output neuron, and you can read the voltages. This is just to demonstrate really the flow, how to get from SNN torch to the Spinnaker 2 chip. And you might need some more useful data and convert input data accordingly to get some meaningful output here. So this was that example here. And there's another quick example here for the DNN scheduling on Spinnaker 2, where I will quickly show you. I will not be executing this on the chip right now, but I will show you a visualization of how this looks like, basically on some log data. I will simply not execute this because it's taking a while to send back and forth data. If you're really interested that this is actually working, you can come to me later. But I will quickly show you a visualization here, how the scheduling of non-spiking neural networks actually looks on the chip. And I created a little visualization here because it's always hard to, if you have the chip and you have something like scheduling, it's always a bit hard to visualize this and say, yeah, this is cool stuff running on the chip. This is why I created this visualization here. And I need to check out that I'm on the correct branch here. Okay. And so I'm now building this application here. And I'm now executing this. So this is a nice little GUI. And what you can see is a previous version of the scheduler. You can see that this is still using this output tiling where I define my square tiles, create partial products, and then I accumulate them. These are my two input matrices here. And you can see here what input tile is mapped to which PE. There's also some things that can be optimized. For example, you may have seen previously in the Spinnaker 2 demo that there is shared SRAM within these groups of 4 processors. So it's actually not necessary to transfer the data to 4 processors. I mean, the same amount of data, you just need to transfer to one of them. So there's a long list of optimizations that can be done for the scheduling. But the idea here is really to get the first version running and then basically implement these modifications. You see what processor, or you don't see the actual numbers, but you will see that each tile is loaded to different processors. And then, for example, on processor 1, you will multiply this tile with this tile. And on processor 2, you will multiply, or let's take it like this. On processor 5, you will multiply this tile with this tile, for example. Yeah, and by this, you will create your partial products and then accumulate them together into the final output here. And this is now a visualization of the actual processors. So I will start the visualization in a second. And what you will see on here is that we don't use all Ps, we just use a couple of them. And this is a color map of the states which each processor is running on. And you can see here that each tile is loaded to 4 processors. And these final output tiles, this is 4, 8, 12, and 16. So each processor, 4, 8, 12, 16, and so on, accumulates the tiles of 3 other processors. And this is what you will see here. So there's always one processor fetching from the other processors. This is such a group here, for example. So this processor 4 would fetch from 5, 6, and 7, and then accumulate. And you will see that the processors 5, 6, and 7 just run their matrix multiplication of the tile, and then they're done, because only processor 4 will fetch the results and accumulate them locally. And you can also see the states machines of such an accumulating worker, so 4, 8, 12, and 16, and a non-accumulating worker. You can see this below here. And I will now start the visualization. And you will see that they all start from this idle state. It takes a couple of seconds for this to run, so we have some time to get used to it. And you now see the execution of the matrix multiplication. And you see that now this one is accumulating and these ones are basically finished. Yeah. And after, they are fetching, yellow means fetching, and now they are accumulating the results. And you can already see, so this is according to the time here. You can see that the accumulation takes rather long. This is why I kicked it out in the current version of the scheduling. Now it's accumulating again, it takes some time. So I'm avoiding this right now, but in this version, it's still the case. And what you can also see when these, while these are still fetching here, the first ones already start accumulating. So it's a bit of an asynchronous scheduling. So I'm not waiting for all PEs to finish the same state, but it's really processor by processor. As soon as this one is finished, and then it starts the next state, basically independent of the other operations. And what you see now is that all the processes have finished. So this layer would be complete here. And this was a small visualization of the scheduling.
Maybe just to remark that this is of course slowed down, right? This is not.
Yes, this is not in real time. Yeah, this is the microseconds here, though. So this would be running below 1 millisecond. Oh, sorry, below 10 milliseconds actually. That you need to add 0. Yes, so this was a short visualization here. And we're skipping that one for the moment, the demo on the big board. So there's a drug discovery use case. I will try to set it up. We had some issues there with the power supply. I will try to set it up during one of the next days, and you might take a look here. And yeah, there's a couple of publications here. For example, this one was from a NIRIPS workshop 2023, where we basically it's a general publication on the Spinnaker 2 system. There are a couple of publications related to the Spinnaker 2 system. The QR codes, I will still update them. So if you try them now, they will not work, but in the uploaded slides, they will work. I still need to upload the codes and correct them. And yeah, I think Christian will take over now for current development in Access.
Yeah, okay. Right, so let me wrap this up really quick. It's only 2 slides. So that's a current picture of the machine in Dresden. So still a lot of empty, you can read it out, but there's still a lot of boards missing. So what we have at the moment is essentially about one of those racks filled, so 90 boards. We did have some issues with the manufacturer of the boards, reliability stuff. So we switched the manufacturer, so that's not gradually getting ironed out. So basically this will now until year end kind of dump. Boards will come in, we test them, we slot them in. So that's the idea. Yeah, just for fun fact, yes, I did my bit. Setting up, so this is really setting up the frames, the backplane, power supplies, communication, and whatnot. Next slide. And this is maybe the more content one. So timeline across software, hardware, and support. So let's start with the first one. From about March, April, right? Everything that Tim showed you, software-wise, single chip, full stack. I mean, Python for most stuff, C++ for the more advanced stuff. The boards are also in operation, but they're still at the bare metal stage. Hardware-wise, there's a slight problem. Some new export regulations in Germany came into force, which basically means that TU Dresden would have to navigate forms just to get those boards loaned to everyone. So they wouldn't even want to try it. They just said, you don't get these boards out of Germany. So those are okay, right? Bring just for the workshop. There is a couple of boards that are still running around in labs, and TU Dresden actually told me get them back. So the preferred mode at the moment, right? We've got this rack operating at TU Dresden, is cloud access. Yeah, you write a mail to Bernhard, he gets your login, and then you can get going. Support-wise, also, that's a slight change from Spinnaker 1 from Steve, right? He used his PhDs on support for all the external use cases. I'm sorry to say that's not what PhDs are for, right? They need to do science. So I'm not going to do that. This is actually one reason why the startup is there. The startup has basically taken over the entire software stack. So you get real professional grade software there. But of course, then again, workshops like here, right? We were there and you ask us questions, that's totally okay. But anything beyond that, I mean, like we do with a commercial product, pretty please in your project, put in, you get quotes from the company. It's not that expensive. You just get professional support, right? You get support tokens, and which is basically a couple of man hours from the support engineers at Spin Cloud Systems, and you can get direct interaction with them. So yes, that stays the same. Support will always run like that. And of course, as Tim showed you, there's lots of resources on the web you can also read yourself into, that you don't need to bother with the support for just the small problems. Right, from October, first release of the board level software. Then we're going to split the cloud access. So kind of the small scale academic cloud access will still run via TUT. The larger scale or commercial applications via cloud at Spin Cloud Systems. So we just had to make a split here. So for you guys, probably it will still be mostly the academic support. But again, if it gets commercial, if it gets lots of hours, then it's going to be quite competitive rates. I think like €2 per board hour or something. But then this one here. Then basically from end of this year, we're actually delivering the first 16,000 chips. So that's about 4 racks or 3 3/4, which are already 90% sold out. So basically, you ask me why 60,000 chips? This has to do with some very weird funding restrictions at TU Dresden. The first production run was limited, right? So those are already gone. If you're fast and order boards, then you can probably still get something out of those 10%. And this, as I said, we will deliver to Manchester in December, and then probably to Leipzig, Göttingen, Munich, Sanya, or Sanya also gets some in December, and then goes on until basically June or so, before we've got this all delivered. At the same time, you get a release of the rack scale software, and then basically from September 25, release of the full machine stack plus next production run, right? So this production run will mostly be the 48 chip form factor. From September next year, you get form factors 1 chip, 4 chip, and the 48 node boards, the big compute boards. So that's the PCBs we're currently developing. So yeah, key takeaways: hardware load boards unfortunately no longer possible via TUT. Go for cloud access. Support always commercial grade level by SCS. Sorry, my PhDs, they aren't project financing, right? They need to do stuff for the project. It just doesn't make sense, right? So providing support for free at the same time that they actually Tim here, for example, is a prime example. He's building up software stack. He is actually supposed to be doing medical data analysis on Spinnaker, but we figured we need to do all this software stack before he can get started. Yeah. As I said, some leftover hardware from the current production run if you're fast. And maybe also one key takeaway is be fast also for this one here. We're taking pre-orders now, and this stuff will be delivered then from September on a first come, first served basis, right? So write it in the project, or if you've already got money, contact Spin Cloud Systems. Maurice there is the head of marketing, head of sales, and basically get a quote integrated, right? Or again, just sign the quote, order it, and then you might get one of those if you're interested in 48 node boards, or definitely you will then get one from the next production run. The next production run actually incorporates also a couple of bug fixes. So this is still the original chips. There is some not really critical stuff, some small errors in the DMA that we're now working around in software, for example, and those will all be fixed in the next production run.
Hey, sorry, question?
There's a question.
Yeah. I'm sorry. I think in the slides that he presented earlier, I was seeing drug discovery on Spinnaker. Did you actually show a presentation on that? Probably I missed it. I didn't see anything on that.
I think drug discovery.
Yeah, on Spinnaker.
Let me check my mails because I will show a poster from Florian. One of my colleagues has been working on that. Might be more efficient to look for drug discovery. But if you guys are just interested in the drug discovery, there is a paper in the making. I think actually 2 papers will be out by this fall, right? So you can also read it up.
Okay.
Find it quickly, we can take a look. No, it's just information for running the demo slides. Okay. And hopefully no two-factor authentication. Okay, this looks good. This is probably the poster here. Yeah, so a colleague of mine, Florian Kelber, has been working on this in collaboration with the University of Leipzig. And okay, it's the slides. So yep, you can do some power optimization here. It's actually running on the 48 node board now. Let me check again if I find the poster here. But the long and the short for the current drug discovery is it's basically small molecule receptor matching. So you've got this huge database, 100 billion compounds that you need to scan through. You've got a small MLP, so it's really tiny network. And that scans, the network encodes the receptor profile and basically matches up. So these molecules from the database get pre-processed before. So there's actually pretty sparse markers. So that also fits neatly to Spinnaker.
and then we just run the database past the past these matching markers, past the matching MLPs, and that's basically just pre-scanning. And there's a number of refinements that we're thinking about stitching in, like generating the molecule database directly on the machine, actually having multiple hierarchies of switching on and off parts of the network. So if we're sure that a particular family of molecules actually doesn't fit at all to this receptor profile, then we just scratch it and start with the next one. So kind of dynamic reprogramming. And of course, the next things for the drug discovery, as I said, is using the probabilistic computing, the random sources, to do electron density computations, so kind of a Monte Carlo sampling. And a lot of that stuff is actually, again, also kind of CPU workloads that we're also trying to optimize. Yeah, so that's pretty much it. As I said, it's at the moment it's kind of getting started on this, and there is any number of refinements we can basically stitch in. So we are fast at the moment than the GPUs. What we're aiming to do is also being more accurate by adding all these physics-based simulations, right? We've got the X, the log accelerators, and whatnot. So we can actually do stuff like finite element methods on the molecule. So this will all get stitched in. Yeah.
Just a simple question. I feel like there's quite a few sort of points of contact, and maybe you write something up to run on Spinnaker. And then you could do this low level thing, the Pi Spinnaker near graph, or as an N-torch. So if I just had a network with defined weights and defined leap rates, specific sort of topology and architecture, where would be the easiest place you think for me to write that such that it most likely will work?
For me personally, we still have to figure this out within the project.
This is something that
Exactly. Yeah. Because I've been mainly working on scheduling for classical deep neural networks.
Yeah.
But I'm getting more and more into the SNN stack, and I think the easiest way, if you have a CNN, is currently not via SNN torch, because it's not supporting this conversion from convolution layers to NIR. So we could use MLPs for that, or to define your network architecture in the NIR configuration, because
Correct.
from NIR to Spinnaker 2, you can convert the convolutions and so on, and then take the weights and apply them to the projections there. This would probably be the easiest way right now. With the additional information that this might actually, another way might actually be more efficient. We have to figure it out.
Okay, so a good starting point is maybe get familiar with writing graphs in near and then see.
Yes, probably.
Yeah.
And
I mean, also, of course, the PyNN interface is pretty far along, and PyNN, of course, on the one hand, allows you to generate populations kind of in connectors randomly, but it also allows you to just define a connection matrix between the neurons and then download it, right? So I think that actually should also work already on Spinnaker 2.
Yes, and for as an N-torch for this conversion, a colleague, Céline Arfa, has been working on integrating convolutional layers and so on into this conversion from as an N-torch to near. There is currently, because this was, I think, in March, and it was not integrated yet in the main branch. And there has been some modification in the code, so she needs to make sure that her code still works with the new modifications in SNN Torch. And I've already talked to Jason. Once this is done, then he will integrate it into the main branch, and then you can also convert models with convolution layers and so on directly from SNN Torch. Yeah. Okay.
Other questions?
No. Yeah, thanks a lot.